Now, if we look at this equation that we have obtained for a position as a function of x, it's omega t plus phi. So it's a cosine function. So if we plot it on this axis, we have the time here, and this will be the displacement x. So the x is in this direction and the time is in this direction. Then this would be a cosine function, and it's not starting from here. This is not x t equal to 0, but t equal to 0 maybe somewhere here, and this little distance would be our plus or minus of what we call a phase shift. So if the phase shift is 0, then it's simply a cosine omega t function. But if there is a phase shift, then we would start a little bit away from the peak value. So the timer started a little bit here. It did not start when the mass was at the end. Now we make a few definitions. We'll see that the distance from here to here in terms of time, so this time period from here to here, written as a capital T, that is the time period, and that is the time it takes for the mass to make one full vibration. Now, in terms of the mass that's moving back and forth, this is something like the mass being here, the spring being like this, the mass is here and is pulled down to this position and released, so it will go up and down between these two positions. So it goes at most up to here and down at most up to here. So it keeps oscillating back and forth, and as it's oscillating, the time axis goes this way. So if we consider this to be an oscillation like this, and the time starts moving, it will go like this and follow a sine curve. So this keeps moving up and down, the time axis keeps going like that, becomes like that, so it becomes a cosine curve. Now the time between when it's at the top, reaches the bottom and comes back to the top, so from here to here, is called the time period. When it starts from here, reaches the bottom and goes back, that is one cycle. So one cycle is from here to here. It could also be from here to here, and this could also be a time period. Well, actually it could be from here to here. So it starts from one phase and reaches the same phase after moving one full cycle. So in terms of the angle from here to here, it's 2 pi radians, or 360 degrees. And then the cosine becomes the same as what it was. So whatever is the value of cosine here, after 2 pi radians, it becomes the same value. So that's the time period. And we also define the frequency, which we write as an f, and that is, if you have a point here, then how many waves will cross that point in 1 second. So that is equal to the number of let's say this is the crest, or number of cycles that are completed per unit time, which is normally a second. So the number of cycles per second is the frequency, and it's written as per second, or it's also written in terms of a hertz, and the symbol for hertz is Hz. The unit for time period is a second, and it turns out that the frequency is equal to 1 over t, or t is 1 over f. Now we have another thing to define, and that is omega, and that is the angular frequency. So when we have one complete cycle, let's say starting from here and going back here, then the angle moved is 2 pi radians. So in 1 second, if it covers 2 cycles, then there will be 4 pi radians. So the angular frequency is 2 pi times the number of cycles per second, and the units would be again second inverse, or you can say radians per second, but radian may or may not be written. So it's radians per second, or it's simply per second. Now let's have a look at this equation again. So we have the position, and we have a derivative of the position. So this is the rate of change of position, which means that how rapidly this is moving downwards. So let's suppose at some instant of time it's here, the mass is here, and it's moving downwards. So this is its position x, that would be like here, and this would be its velocity moving downwards with some speed. So what is the speed? That's simply dx by dt. So this becomes the speed of that object at any given value of t. So this becomes the velocity of the mass as it's going up and down. So here the velocity is downwards, here the velocity is upwards, and we can get the correct sign from here. And as it's moving, it will slow down when it comes here, stop for an instant, and then start moving downwards, and then it will slow down and stop here. So there is an acceleration. Well, we saw the acceleration also here, so it will have an acceleration which depends on x. So this is the acceleration, which is a function of x, and this is a linear function of x. So the acceleration will be 0 here and maximum here from this equation. So the acceleration, when x is 0, the acceleration is 0. When x is maximum, acceleration is maximum. So when x is positive, the acceleration is negative, which is downwards. When x is negative, the acceleration is upwards or positive. And the acceleration is maximum here and here, or here and here, and also here, and the acceleration is 0 at these points. So this equation, the second derivative, gives us the acceleration. So that's the velocity, and that's the acceleration. Now the maximum velocity will be here as it's passing through the center, because it's accelerating downwards, and the acceleration stops here and acceleration becomes negative. So it keeps on increasing speed up to here, it starts decreasing the speed here. So the velocity is maximum as it crosses this, downwards or upwards. The value of the velocity here is, or the maximum velocity will be when we maximize this, and this is maximized when sine theta is 1, and so the V max is going to be, and this is 1, is going to be minus a omega, or the magnitude is going to be simply a omega. And the maximum acceleration, again the magnitude, is going to be when cosine theta is 1, so it's going to be a omega square. So these are the maximum values of the maximum velocity and the maximum acceleration. Now to find an equation for t, we say that at t1 the amplitude is maximum, or x is right here, and then after some time, one time period, it makes a full cycle and it's back here. So at t1 it's here, and at t2 it's here. If this height is x1 and this is x2, well then x1 will be the same as x2. So let's write the value for x1, and we will have x1 is going to be a cosine of omega t1 plus phi. Okay, that's the value at t1. And x2 is the value cosine omega, the t is going to be t plus a time period, because from here to here is one time period, so we'll add that here, plus phi. and of course x1 equals x2. So because these two are equal, therefore the difference between these two has to be 2 pi radians. And so if you add 2 pi here, omega t1 plus phi plus 2 pi radians, that will become equal to t plus phi. So this will be equal to this plus 2 pi radians, because it goes from here to here is 2 pi radians. And then we can cancel out the phi's, and we can say that would be t1. So omega t1 plus 2 pi equals omega t1 plus omega t. And the omega t1 will cancel, and we will have omega is 2 pi over t. Or we can say that t is 2 pi by omega. So the time period would be 2 pi by omega, and omega, if we recall, was k over m. Omega square was that, so it's the square root of k over m. So when k is big, omega is big, and the time period is short. And when mass is large, omega is small. When omega is small, the time period is large. So a heavy mass here would cause it to oscillate slower. Now we can do one final thing, and that is substitute omega in here, and then t will become 2 pi over omega, which is square root k over m, and that will become 2 pi m over k. So that becomes the time period. So the time period for oscillation of a spring mass system becomes equal to 2 pi m over k.